So yesterday we talked about how to do Riemann sums, and today we're going a little bit more abstract, or these might be called formal Riemann sums. But we're going to think about things a little more analytically. So this says, given a function f, which is non-negative and continuous on a closed interval a to b, let a to b be partitioned into n subintervals that, although not necessary, can be taken of equal length. So we've had different problems where delta x is the same. We've had other problems where they give us a table usually, and delta x changes from piece to piece. So what is the length of each subinterval? That's asking what is the little formula for delta x. So delta x in general should be b minus a divided by however many subintervals you want. Using rectangles to approximate the area of S, the region under the curve, to the axis on AB, we could choose any number of xi in a subinterval to find its height. Basically, like, you don't have to choose an endpoint as your starting point. You don't have to make it a midpoint to make the height of that rectangle. So what is the area of each individual rectangle? Well, the width of the rectangle would still be delta x. I'm going to say area rectangle. It would still be delta x for the width, and then the height would be whatever xi you're choosing. So like here you can see here's an xi, and we don't know how that falls in the entire interval. It would be f of that individual x value, x sub I. Approximate the area of f of x by the sum of the areas of these rectangles. So we don't know how many rectangles we have, but it's the sum of a certain number of areas. So we like to note, sort of use the notation S sub n, the sum of n rectangles, is equal to, every rectangle has this delta x for its width, and then the heights vary just like they did with our regular Riemann sums. We would have like f of x1 plus f of x2 plus dot dot dot, all the way out to f of xn. Sometimes x1, x2 to xn, those are like starting at A. Sometimes those are midpoints, or they could be sort of any arbitrary point that we pick. Use sigma notation, we get to use a Greek letter, to write the sum of products more simply. So instead of writing it out, especially if this is like, 100 terms long or something, we wouldn't want to write all of that out. And the dot, dot, dot isn't really good enough. So we would say S sub n is equal to the sum, which is, here's a capital sigma, it kind of looks like an E, of delta x times f of x sub I. So what we wrote back here, generic area formula. And then we need to say how many terms we're taking the sum of. So I, the little subscript here, could start at 0, and it should end at n. And so this is our formal definition or abstract definition of a Riemann sum. A sum of n products. So again, sigma notation over here in this box. Sigma means to add all of these separate terms. I put the delta x first. You can see it's written differently here. That doesn't matter. Start with, start with I equals m. In this case, I wrote I equals 1. We may be given a different starting point. And then end with n. So why wouldn't we start with 1? It would be like possibly that causes us to have a negative exponent or something, kind of depending on what the terms are. You'll see as we go through some of the bookwork. So if we practice a couple of basic summations, we're then going to come up with some properties. The properties you're going to want to memorize. When you're doing your homework, you're definitely going to want to have this sheet out when you're doing your bookwork. And so these are things to kind of study. How often does this pop up on the AP test? It's definitely not all over the place, but it could pop up and it will help us down the road as well. All right, so what if we want the sum from 1 to 6 of just I. So that would mean you're plugging in these numbers in for I. So that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6. So 3 plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. So that sum would be 21. I plus 1 squared. So now we're going from 0 to 3. So here's where we don't have to start at 1. So 0 plus 1 squared is 1, plus 1 plus 1 squared, 2 squared is 4, plus 2 plus 1 is 3, squared is 9, plus plug 3 in, that's where we're ending, 4 squared is 16. 5 plus 9 is 14, plus 16 is 30. Now, these weren't too bad to do by hand. 6 terms added together, or 4 terms added together from 0 to 3. If those numbers get large, then the number of terms gets large, then you're going to want to have more of a formula to figure out what to do. So if you have some sort of constant being multiplied by the thing you're plugging into, you are allowed to pull the constant out in front. So if this would have been like 2i, I could have said 2 times the sum of all of that instead of multiplying each term by 2. So that's a property. And if we are adding up just a constant term, so like the sum of 5 from 1 to 3, that would be 5 plus 5 plus 5. So it should equate to just n, the number of terms you're supposed to have, times that constant. Okay, I'm going to wait on this one and this one. So let's go up to here. The sum from 1 to n of a plus or minus bi. You are allowed to, if you're adding or subtracting 2 different terms in here, you're allowed to take the sums separately. That's sometimes easier. And that would be if there's no exponent out here. We're just saying the sum of a plus or minus bi. So I can do the sum of ai from 1 to n, and then I can add or subtract to that whatever I get for the sum of bi, and combine those answers after. All right, here's a generic formula for the first example that we already did. So the sum from 1 to n of I should equate to n, which is the number of terms, times n plus 1 divided by 2. Let's see if that works for ours over here. Let's check this property. So it should equate to 6 was our n. So it should be 6 times 7 divided by 2. 42 divided by 2 is 21. So that's kind of nice. It wasn't hard to add up 6 terms, but if I would have asked you to do the sum from 1 to 60, then that would have been a bit more cumbersome to write out all of those terms and correctly add them together. So it would be easier to say, oh, it's going to be 60 times 61 divided by 2. Okay, so this is a handy one to memorize. What if we have the sum of I squared from 1 to n? Again, I squared could get pretty cumbersome if you have more than just a couple of terms that you're adding together. So it's going to equate to n times n plus 1 times 2n plus 1 over 6. And by the way, I've never actually looked up the proofs for these. I guarantee there are proofs somewhere out there on YouTube if you're really interested. Add that to a fun weekend activity. So, okay, that's, again, just something to memorize. If I'm supposed to be adding up the squares of terms, I could just do number of terms times n plus 1 times 2n plus 1 all over 6. And a similar formula for I to the third. Now, I'm going to admit I don't have these memorized right now. I haven't done the homework, so I haven't practiced them. And, I teach this every other year, so we don't use this a ton. It drops out of my brain every year. So I'm kind of in the same boat with you. I'm seeing these formulas. I'm going to do my best to study them and memorize them. It's 3 things, right? I guess you could say this needs to be memorized. I think the 2 properties are pretty intuitive. We can pull a constant out in front. We can sum 2 different terms. So we're memorizing 3 or 4 things, depending on if you don't have this one memorized. Okay. So what are we going to do with all this stuff? We're talking about like summation. What does that have to do with Riemann sum? So remember, we are talking about adding up rectangles underneath a curve. So I want to evaluate the Riemann sum for f of x equals x squared on the interval 1 to 3 using 4 subintervals of equal length, where xi is the right endpoint of the ith subinterval. So the Riemann sum is, here's some different notation for you. We're supposed to use 4 subintervals, so let's call it S sub 4. Remember back here we said S sub n. And it's going to be the sum from 1 to 4, because we're talking about how many rectangles we have, not our interval. So we have 4 rectangles of delta x f of x sub I. It's a good idea to write this general thing first. Okay, so what can we fill in? We can start with f of x, we can start with delta x. Off to the side here, delta x is equal to 3 minus 1 divided by 4, so 1/2. So now I know that the Riemann sum is going to be the sum from 1 to 4 of 1/2 f of xi. And remember, you're allowed to pull the 1/2 out in front. So here's where we're kind of thinking, okay, what is this f of xi? Now here it tells us f of xi is the right endpoint on the ith subinterval. So we're going from 1 to 3. Let's mark off our area of interest. We're supposed to start on the far right. That's the first x sub I. And we said we were going to go every half unit. So we're going to connect from 3 over to 2.5, from 2.5 over to 2, from 2 over to 1.5, and finally 1.5 over 1. All right, so that means that I'm going to have 1/2. I'm going to take out the summation symbol because I'm going to actually add the terms together. Whether you start on the right or the left is up to you. I've been kind of getting in the habit of, if I'm supposed to start with a right-sided subinterval, I'm going to do f of 3 plus f of 2.5. I should probably do. We're going to be squaring, so I know I wrote 2.5. 5 over 2 probably be better. Plus f of 2 plus f of 3 over 2. It's fine if you want to start with the 3 over 2 term first, but this just kind of helps me make sure I don't accidentally use f of 1 when I wasn't supposed to. All right, so this is a normal Riemann sum like we've been doing. We're just plugging into x squared, so 9 plus 25 over 4 plus 4 plus 9 over 4. And I've done the math ahead of time to kind of save time a bit here. So I'm getting that the Riemann sub for 4 subintervals, the sum of 4 terms, is 43 over 4. Now, remember, one thing I want to add to this before I box it in. That's the Riemann sum. Is this the exact area under the curve? No. This is the approximation for the area from 1 to 3 of x squared dx. It's approximately equal to the Riemann sum of 4 terms, which is 43 over 4. And I know that that is overshooting the area because I can see in my picture that that's giving me more area than what I have under the curve. How can we make our approximation better and better, more accurate? Assuming we have equal subintervals again. Well, the more subintervals you use, the more accurate it's going to be. So allow n to approach infinity. The number of terms should approach infinity so that delta x can approach 0. If we had really teeny tiny little rectangles, then we would practically have the area under the curve. So that's where we get into our theory here. The area of a region S that lies under the graph of a continuous and non-negative function, it needs to be above the x-axis, is the limit of the sum of the areas approaching the rectangles. So we can say back to limit notation here, we can say the actual area is the limit as n approaches infinity of s sub n, which is equal to the limit as n approaches infinity of the delta x times each of those terms. Or if you don't want to write all of that out, remember we have our nice shorthand sigma notation. So we have the limit as n approaches infinity from 1 to n of delta x f of x sub I. So let's find the exact area, not approximated, the exact area, which means I'm going to have to use limit notation. Using limits of Riemann sums. And again, this only works if f of x is above the x-axis, greater than 0, and continuous on whatever interval you're looking at. So we're looking at 0 to 1. Okay, so let's start just by writing out our formula. So the exact area is equal to the limit as n approaches infinity of the sum from 1 to n of delta x f of x sub I. Okay, so let's figure some stuff out. Usually I start by saying, well, what is my formula for delta x? We weren't told to use a certain number of subintervals because we're picking anything, right? So let's just say, okay, what is delta x? Delta x, our interval goes from 1 to 0. So it's 1 over n. Okay, so limit as n approaches infinity of the sum from I equals 1 to n of 1 over n f of x sub I. Now, how do I write this f of x sub I? In the previous problem, I was told, oh, x sub I is going to start on the right side of the interval. Well, here it could be anywhere. So we have to figure out what is f of x sub I. X sub I could be anywhere. It could be right here. That could be where I decide to put a point on the graph. Okay, so what does that mean? Well, x sub I, where I placed it here, is a certain distance away from the beginning of the interval, which is 0, right? Like there's some sort of delta x here. And it goes from that interval out here. So we could say f of x sub I would equal whatever delta x is. Remember, it's something really tiny. It's approaching 0. Whatever delta x is, units away from the beginning of the interval. So the interval starts at 0 plus delta x. And then what is I? So I would be, remember, the number of terms that you're at. So this could be the third or the fourth or the fifth or the millionth rectangle. So it would be delta x times whatever I is to get me out here. And this is the x cubed graph. So we're plugging it into that quantity cubed. So we're plugging in 0 plus delta xi into that quantity. All right, you'll do that every time. So you'll start at the beginning of your subinterval and then add delta x times I and then plug into whatever your equation is. Well, let's simplify this a little bit. The 0 doesn't need to be there, right? Delta x we just said was 1 over n. So now I have I over n to the third. That's the same as I to the third over n to the third. So instead of having f of x sub I in my formula for my actual area, I can now replace this piece with this expression. So I can say limit as n approaches infinity of the sum from 1 to n of 1 over n times I to the third over n to the third. And that could clean up, right? We can multiply these n's. The limit as n approaches infinity. Here's how I like to write it before you get too ahead of me here. Let's put the 1 over n to the fourth out in front. We're going to separate that out. 1 over n to the fourth. And then I to the third. This is where we need to use one of those formulas that I said, like, oh, I don't really have these memorized either. We'll figure it out in a minute. I to the third, back to the previous page. When you're doing the sum from 1 to n of I to the third, it's equal to n squared times n plus 1 squared over 4. So let's sub that in for that I to the third right there. Oh, sorry. Actually, one more step here. I can't sub that in until I actually take the limit. So, or until I actually do the sum. So one more step here. Limit as n approaches infinity. We're dropping our summation notation of 1 over n to the fourth times the sum from 1 to n of I to the third is equal to n squared, I believe it was. See, I have to go back and look. N squared times n plus 1 squared over 4. So you make that substitution when you drop your summation notation, because you're saying when I sum up all those terms of I cubes, it'll come out to this expression. Okay? And then some things cancel, don't they? Before you take the limit, n squared cancels with n to the fourth, so you have an n squared down there. So you're going to get the limit as n approaches infinity of n plus 1 squared over 4n squared. And now we're back to chapter 1. How do I take that limit? It's a limit as we're approaching infinity, which, remember, you should just be thinking is a horizontal asymptote. This is a tie because it would be n squared over 4n squared. So the limit is equal to 1/4. So finally, the area, the actual area, is equal to 1/4. Another way to write the actual area instead of A equals, what we're saying is the integral from 0 to 1 of x to the third dx is equal to 1/4. And you can check that answer. If you know how to do definite integrals, if you've done that in physics or AB last year, you can kind of check your work and say, oh yeah, it would work out to be 1/4. This is basically the proof for how definite integrals work. Okay, I think I'm going to have time to do these next few before office hours start. So here's another one. We're going from 1 to 2. Start off the same way. We want the area to be the limit as n approaches infinity of the sum from I equals 1 to n of delta x, f of x sub I. I always like to start here so that I can give myself kind of the same steps over and over. First, find delta x. We're on the interval of 1 to 2. So 2 minus 1 over n is, again, 1 over n. That's often what delta x is, but not always. We might as well also find f of x sub I. Remember, this will always be plugging into your function. So here, before the function was just x cubed. Here I have 4 minus x squared. So 4 minus something squared. The something will always be starting at the beginning of your subinterval. In this case, it's 1. Adding delta x times I, because that will get you to like wherever this delta x is. I don't know how many rectangles I'm going to get to before I get there, but that's why we say times I. Okay, and then simplify that. 4 minus, we know delta x is 1 over n, so this is 1 plus I over n, the quantity squared. And if you want to square that out right now, you could. It'd be 1 plus 2I over n plus I squared over n squared. That would be 3 minus 2I over n minus I squared over n squared. We have two things to plug in. So we have, for delta x, we have 1 over n. For, oh, that's great. For f of x sub I, we just blew Microsoft OneNote's mind here. Okay, we have 1 over n. For f of x sub I, we have 3 minus 2I over n minus I squared over n squared. All right. So what did I do last time? Well, last time I kind of separated things out, but I don't think I want to think of factoring this out. Since I don't have an easy way to like remove the n squareds, I'm going to go ahead and distribute the n through. Okay, so I have the sum of 3 over n minus 2I over n squared minus I squared over n to the third. Okay, now we're going to go ahead and take sums. So we're going to drop the summation, but we have to keep our limit notation. 3 over n is a constant, right? 3 divided by n. Go back to your rules back here. A constant, the sum of a constant will turn out to be n times the constant. So this first term becomes n times 3 over n. Minus, I'm going to write 2 over n squared. And then this I, the sum of just a single I, go back here, right there, becomes n times n plus 1 over 2. So 2 minus 2 over n squared times n plus 1 over 2. Minus, I'm going to write 1 over n to the third, times I squared, rolling back up, becomes n times n plus 1 times 2n plus 1 over 6. N times n plus 1 times 2n plus 1 over 6. Okay? Well, you can clean some things up here if you'd like to. I think that would be smart. We have the limit of, as n approaches infinity, of 3 minus, those 2's cancel out. We should be n plus 1 over just n, because the n over n squared reduces. Minus, nothing cancels here, so n times n plus 1 times 2n plus 1. Oh, sorry. One thing cancels. The n cancels, right? That n cancels with one of those over 6n squared. Finally, we can drop limit notation and take the limit. The limit as n approaches infinity of 3 is going to stay 3. Minus, this is a tie here, so minus 1. We would have 2n squared over 6n squared, so minus 1/3. All right, so 9 over 3 minus 3 over 3 minus 1 over 3 is positive 5 over 3. So again, what this is saying is the area from 1 to 2 of 4 minus x squared dx, its exact area is 5 over 3. So again, this is basically think of this as the limit definition of a definite integral, just like we did limit definition of a derivative. All right, the last one I have to save for a new video because I've got some people coming in for office hours. So find the second video linked below this one.